Welcome, ladies and gentlemen, to Integrated 2 Math. In today's episode, we will be discussing Chapter 9.2.1, which is Quadratic Inequalities. Pretty complicated topic here. Before we get into quadratic inequalities, I do want to take a minute and review the linear inequality with you, because it's something that we are all familiar with, and it's procedurally inequality. Procedurally, it's pretty easy, but conceptually, it can be a little dicey. If I give to you something like 2x minus 1 is less than 5, it's pretty easy to do. I mean, what you would do is you'd add 1 to both sides. You'd add 1. So I'm going to actually give myself a little bit more space here on this one. You'd add 1 to both sides, and you'd get 2x is less than 6. You would then divide by 2. Oops, I got to move this thing up. Divide by 2. And you get x is less than 3. And what you would do is generally you would draw like a number line. You would draw a number line like this. And you'd mark down a 3. You'd know there was an open circle, and you would just put an arrow to the left like that. For all values less than 3, this statement is true. Pretty simple. And so what I'm going to do is I'm actually going to define what each piece is doing. So what I'm going to do is I'm going to go and look at this 2x minus 1. Real quick. I'm going to look at him as a separate function. I'm going to call him y equals 2x minus 1. And then this guy here, 5, I'm going to call him y is equal to 5. Now, whether you were aware of it or not, every time you solved an equation, what you were doing is you were solving a system like you did back in Integrated 1, where you would set the two y pieces equal to each other. You would get the 2x minus 1 is equal to 5, and you would solve, you get x equals 3, or whatever. And what this was the x coordinate of the intersection between this 2x minus 1 and this line of 5. So real quick, just to define what these things are, 2x minus 1 is a line that has a positive slope like this. So on a graph, 2x minus 1 looks like that. 5, on the other hand, is a horizontal line, right? When y equals 5, it's just going to be 5 all the time. And what we'll find is that the intersection between the two happens at x equals 3. So let me show it to you in this calculator here. I've got my calculator up. I got 2x minus 1. I'll graph him. So you see, notice the blue graph right here. The blue graph, it's going diagonally up, just like our interpretation of this purple, just like it did. So then I'm going to set another function here. I'm going to call it 5. And notice the red function is horizontal, exactly like we interpreted with this version that's actually in sky blue. So from here, let's see what happens. I'm going to go to Menu, Analyze Graph, and this is a good chance to kind of learn how to use a graphing calculator while we're at it. So I'm going to look for intersection, which is going to be where the two graphs intersect each other, where they touch or where they meet. The lower bound is going to be on the left side of the intersection point, so obviously I'm looking for right here. I can do however far left I want. Right bound or upper bound is going to be to the right of them, and notice the coordinates here, 3, 5. 5 was obvious, that's the y coordinate, but 3 is the x value of the point of intersection, which incidentally is the same as our answer here. So x being 3 is the x coordinate of the point of intersection. So how does this help me in a linear inequality? Well, remember, the original problem says 2x minus 1 is less than 5. So what they're saying is that my diagonal, my diagonal line is less than my horizontal line. Now, when I say less than, right, when I say less than in an xy kind of way, right, I'm going to look at him as my first function here, my y1. I'm going to look at him as my y2, which is my second function. So my diagonal line, if I compare them as y's, y controls the up and down motion on the coordinate plane. So what they're saying is my diagonal line is underneath my horizontal. My diagonal will be underneath my horizontal as long as x is less than 3. So let's go and type that out. That way we know what we're saying here. Remember, the significance of the value of x being less than 3 is that the diagonal line the diagonal line, I'll even put this in a different color. I'll put it in green. Or I'll put them in white, actually. The diagonal line, 2x minus 1, will be underneath the horizontal line of 5 as long as x is less than 3. That's what this statement is saying. Now let's verify if that's actually true. We'll go back to the calculator here for that. So remember, the diagonal line is in blue. So remember, the blue, we're going to try and find out when the blue is underneath the horizontal line, which is in red. So again, blue underneath red. There are portions, if you look at this graph, where the blue is below or underneath the red. And if you look at the point of intersection here, look at the point, it's 3, 5. If I move a smidge left of the 3, notice how the blue is underneath the red. If I move totally to the left, like way to the left, the more left I move on the blue, the more down I have to move on the blue, right? Because I'm traveling on the line. As long as I'm traveling on the line to the left of the line, I will be going down the line, which makes it below the red line. So, in all purposes, the inequality is saying the diagonal will be below the horizontal for all values of x that are smaller than 3. I'm hoping that makes sense to you. If not, I am always available for questions. But this is really just a review. This is really just a review. In fact, I don't want to get rid of those just yet. It's really just a review because quadratic inequality is really what we're trying to study. So here's the thing, is that this x value being less than 3 will be always true for this particular statement here, the inequality of 2x minus 1 being less than 5. And that's because the sheer nature of linear problems means that they will not be changing direction. This 2x minus 1 right here, his slope is 2. He's going up 2 to the right by 1 for the rest of his life. He can't change his destiny. This 5 here is always going to be horizontal and flat. He cannot change his destiny. That's why these linear inequalities are always so easy. Once you find a number, then what you do is you just say, whoops, as long as we're greater than that number or less than that number, then we're all good to go. Well, that's not always going to be the case anymore, because as you all well know, a quadratic function, for example, x squared minus 8x, let's see here, plus 12. If I want to compare him to say greater than or equal to 0, we all know this function right here. He's a parabola. He looks like this. This 0 right here, well, he's a horizontal flat line at 0. In fact, he's on the x-axis, right? He's on the x-axis. Well, unlike a linear function, a quadratic function actually does change direction. It's going down, and then right here it stops, and then it moves back up. So our inequality is going to be a lot more complicated this time, because what I'm going to do is I'm going to try and find out when is this parabola going to be above this x-axis right here. So in fact, before I do that, let me go and just put them into the calculator and see what happens. I'll go and delete these guys. It was x squared minus 8x plus 12. Okay, there's our parabola, and I will go ahead and type in the function 0. Technically, as you guys get more advanced, you'll realize I don't have to do that. I can just use the x-axis as my 0, but it's not a big deal. So notice where the blue graph is above the red graph, and notice where the blue graph is below the red graph. So sometimes we're above, sometimes we're below, sometimes we're back up above. So this is going to mean the problem's a lot more complicated. So how do we take care of a situation like this? Well, what I'm going to do is I'm going to factor this thing the way I always have. I'm going to factor him. So by just going for it, I get x, not x squared, I get x minus 6 and x minus 2. Now from here, once I get this far, I'm going to go ahead and set each piece equal to 0. You know how to do that by the zero product property. X is going to be 6 and x is going to be 2. Now what these two numbers are, these are what are known as critical numbers. And critical numbers, unlike actual answers, critical numbers really just tell us where our function equals 0 or is undefined. Now, don't worry about the undefined. You will never encounter an undefined as long as you're in integrated 2. When you're in integrated 3, you will deal with undefined quite often. But for now, don't worry about it. Just worry about where the function equals 0. Clearly, it's going to be at 6 and 2. What I'm going to do is I'm going to go and take the 6 and the 2, I'm going to punch them into a number line here, and I'm going to put them down in numerical order. Now from here, because I'm comparing him to 0, and by the way, I will always compare my quadratics to 0 because the problem is optimized to be seen that way. Since I'm comparing this guy equal to 0, remember, this is my y1 here. This is my y2. And since I'm comparing it to 0, which is such a unique number, I can definitively say that when the parabola is above 0, right? When the parabola is above 0, we can say then the sine of the parabola will be positive, right? Because a y value that is above the x-axis is a positive number. Likewise, I can say when the parabola is below 0, the sine of the parabola will be negative. Now, in this case, I'm using a couple of words, a couple of keywords a few times here. The word sine is really important because this number line here is what's known as a sine chart. And what this sine chart does is it measures the positivity or the negativity of the function in certain places. So I'm going to go and partition these down. I like to draw a barrier right here, and I will put down an x minus 6 and an x minus 2. For now, I'm going to do this a little bit slow. Eventually, there will be ways for you to move faster, but we'll work on going slow first. So from here, what I'm going to do is these regions right here, these regions that I'm going to underline in white, these regions, these are the regions of the graph. And what I have here is this first region here that I just darkened in white is the region that is reserved for all values of x that are to the left of this number 2. And anything to the left of the 2 will be less than 2. So what I'm going to do is I'm going to pick a number that's less than 2, and I'm going to plug it into here, and I'm going to plug it into here. So a number less than 2 is 0. 0 minus 6 is negative 6. But I don't care that he's negative 6 because this is a sign chart and not a value chart. I don't care that he's negative 6, I just care that he's negative. Now I'm going to take that same number, that's 0, I'm going to plug it into x minus 2. 0 minus 2 is negative 2, but again, I don't care that he's negative 2 because it's just a sign chart. He's just negative. This region here that I'm going to, again, darken in white right here is the region reserved for numbers between the values of 2 and 6. So I need to pick a number between 2 and 6, like 4. And again, it doesn't matter what number you choose, as long as it's in between 2 and 6. It's all good. So again, 4 into this function here, 4 minus 6 is negative 2. I don't care that he's negative 2 because it's a sign chart. He's just negative. 4 minus 2 is positive. And now again, this third region on the right side, he's reserved for all numbers greater than 6. So I'll choose a number like 12. Again, it doesn't matter what number I choose, as long as it's above 6. 12 minus 6, positive. 12 minus 2, positive. Awesome. So now, from here, this little rectangular region up here, this is what I call the final interval. This is where you get your answers from. Our answers come from here. And again, these partitions are going to be there as well. So, I'm going to do a couple of connections. I hope this makes sense to you. These two functions here are being multiplied, which means these two functions here in the sign chart are being multiplied, which means these two signs are being multiplied, these two signs are being multiplied, and these two signs are being multiplied. And the signs that are negative and negative, as long as they're being multiplied, it doesn't matter what the value of the signs are, a negative times a negative, regardless of value, will always be positive. A negative times a positive will always be a negative, and a positive times a positive will always be a positive. So, How does this help me determine my answer? Well, for that, I go back to the original problem. The original problem is this. So remember, the interpretation is the parabola must be above the 0. And if anything is above 0, those values will always be positive values. Anything above 0 is always positive. So that's what I circle. And that's where my answer is. But I'm not done yet. I'm going to write my answer in the set notation. So what I say then is this statement here is true. The parabola must be above 0 as long as x is less than 2 or x is greater than 6. Because, notice the arrow. The arrow here says the region to the right of 6 for everything to the right of 6 or everything to the left of 2. So there's your answer. Now before we move on to our next example here, I do want to just relate this back to the graph. So remember, this is all graphical, right? So we're comparing a parabola to the x-axis or a line that's on the x-axis. And we know that the parabola will be above the 0 as long as x is less than 2 or x is greater than 6. So let's take a look at that on our graph. We graphed it for a reason. So notice how, again, we're above sometimes and we're below sometimes. Let's go and find the points of intersection right there. So analyze intersection, lower bound, upper bound. Boom, 2, 0. Look at that, x being 2. I don't think that was a coincidence. Lower bound, upper bound. Okay, here we go. 6. Again, both of our answers are showing up on this graph here as points of intersection. So remember, we were looking for where the blue thing was above the red thing. Notice, the blue is actually above the red for all of my x values that are to the left of the 2, right? If I travel to the left of the 2, I'm going up the parabola. If I travel to the right of the 6, I'm going to the right and up the 6, making me above the line. Notice how we found that without graphing the parabola. So these sign charts are very helpful when it comes to solving for a quadratic inequality without having to graph, because graphing can be a bit of a pain. And so I hope that makes sense. Let me go ahead and clean up the board for our second example. And we're back for our second example here. We've got x squared plus 9x minus 22 is less than or equal to 0. So the way I usually tackle these is I read the problem to myself and I already start thinking, okay, I see a parabola, and I see 0 here, and I want the parabola to be less than 0. So what I'm thinking already is I want to look for my negative final interval because I'm trying to look for where the parabola is below the line. So how do I manage this? Well, I'm going to factor it like I always have. I believe this is going to be x plus 11 and x minus 2. My critical numbers are negative 11 and positive 2. I will put those into a sign chart, and I will get negative 11 here and 2 here. I will partition it down. These problems actually can start to move really fast, and in the next video I'll show you guys a shortcut for this. But for now, we'll go and just do the long cut version. So from here, a number that's less than negative 11, I'll pick negative 20. Negative 20 into the top is negative. Negative 20 into the bottom is negative. In between negative 11 and 2, I'll choose 0. Positive, negative. And then anything beyond 2, I'll choose like 10, positive, positive. So again, I acknowledge that these two functions are being multiplied, which means all of the signs are being multiplied. Plus, minus, plus are my signs. Now you'll start to notice a motif when it comes to these quadratics. They will always follow that pattern. I still want you to do these sign intervals. So again, how do I know which of my final interval to choose? Well, again, I go back to the original problem. The original problem has me finding out where the parabola is below the line. Below the line means negative, right? Especially because I'm talking about 0 here. So any number that's below 0 is going to be a negative value, which means I am locked in between negative 11 and positive 2. So I can say then that x has to be in between negative 11 and 2, and I write my compound inequality like that. And I believe that will be enough to wrap it up for this video. I will be back with some more examples. I'll just do a bunch for you, that way you guys get comfortable with them. As always, please leave comments or questions in the comments area, and I will see you in the next episode.